The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, guys, let's get started. So today we're going to talk about side channel attacks, which is, well, a general class of problems that comes up in all kinds of systems. Sort of broadly, side channel attacks are situations where you haven't thought about some information that your system might be revealing. So typically you have multiple components communicating, maybe a user talking to some server, and you're thinking, great, I know exactly all the bits going over some wire between the user and the server, and those are secure, but it's often easy to miss some information revealed either by the user or by the server. So the example that the paper for today talks about is a situation where the timing of the messages between the user and the server reveals some additional information that you wouldn't have otherwise learned by just observing the bits flowing between these two guys. But in fact, there's sort of a much broader class of side channels you might worry about. Originally, side channels showed up, or sort of people discovered them in the 40s when they discovered that when you started typing characters on a teletype, the electronics or the electrical machinery in the teletype would emit RF radiation, and you could sort of hook up an oscilloscope nearby and just watch the characters being typed out by sort of monitoring the frequency, RF frequency sort of going out of this machine, right? So RF radiation is a sort of classic example of a side channel that you might worry about. And there's sort of lots of examples, lots of other examples that people have looked at, sort of almost anything, right? So power usage is another kind of side channel you might worry about. So your computer is probably going to use different amounts of power depending on what exactly it's computing. And there's been sort of other clever examples. So sound turns out to also leak stuff. There's a cute paper that you can look at that people sort of listen to a printer, and based on the sound the printer is making, you can sort of tell what characters it's printing. This is especially easy to do for dot matrix printers that make this very annoying sound when they're printing. Sort of, in general, it's a sort of good thing to think about. Kevin on Monday's lecture also mentioned some interesting side channels that he's run into in his research. But in particular, here we're going to look at the specific side channel that David Brumley and Dan Bonnet looked at in their paper, I guess about 10 years ago now, where they're able to extract a cryptographic key out of a web server running Apache by measuring the timing of different responses to different input packets from the sort of an adversarial client. And in this particular case, they're sort of going after a cryptographic key. And in fact, many side channel attacks target cryptographic keys, partly because it's a little bit tricky to get lots of data through a side channel. And cryptographic keys are one situation where getting even a small number of bits helps you a lot. So in their attack, they're able to extract maybe about 256 bits or so. And just from those 200-ish bits, they're able to break the cryptographic key of this web server. Whereas if you're trying to leak some database full of social security numbers, then that'll be a lot of bits you have to leak to get a lot of data out of this database. So that's why many of these side channels, if you'll sort of see them later on, they often focus on getting small secrets out. It might be cryptographic keys or passwords. But in general, this is applicable to lots of other situations as well. And one sort of cool thing about this paper, before we sort of jump into the details, is that they show that you can actually do this over the network. So as you probably figured out reading this paper, they have to do a lot of careful work to tease out these minute differences in timing information. So if you actually compute out the numbers from this paper, it turns out that each request that they send to the server differs from potentially another request by an order of 1 to 2 microseconds, which is pretty tiny. So you have to sort of be quite careful, and over a network, it might be hard to tell whether some server took 1 or 2 microseconds longer to process your request or not. And as a result, it was not so clear for a while whether you could mount this kind of attack over a very noisy network. And these guys were one of the first people to show that you can actually do this over a real Ethernet network with a server sitting in one place, a client sitting somewhere else. And you could actually measure these differences, partly by averaging, partly through other tricks. All right, does that make sense? So overall side channel stuff. All right, so the plan for the rest of this lecture is we'll first dive into the details of this RSA crypto system that these guys use. And we'll not look at exactly why it's secure or not, but we'll look at how do you implement it, because that turns out to be critical for exploiting this particular side channel. They carefully leverage various details of the implementation to figure out when are some things faster or slower. And then we'll sort of pop back out once we understand how RSA is implemented. Then we'll come back and figure out how do you attack it? How do you attack all these different optimizations that RSA has? Sounds good? All right. So I guess let's start out by looking at the high-level plan for RSA. So RSA is a pretty widely used public key crypto system. We sort of mentioned these guys a couple of weeks ago in general, in certificates, in the context of certificates. But now we're going to look at actually how it works. So typically, there's three things you have to worry about. So there's generating a key, encrypting, and decrypting. So for RSA, the way you generate a key is you actually pick two large prime integers. So you're going to pick two primes, P and Q. And in the paper, these guys focus on P and Q, which are about 512 bits each. So this is typically called 1024-bit RSA because the resulting product of these primes, which we're going to use in a second, is a 1000-bit integer number. These days, it's probably not a particularly good choice for the size of your RSA key because it makes it relatively easy for attackers to factor this. Not trivial, but certainly viable. So if 10 years ago, this seemed like a potentially sensible parameter. Now, if you're actually building a system, you should probably pick a 2000 or 3000 or even 4000-bit RSA key. But that's what sort of RSA key size means, is the size of these primes. And then, for convenience, we're going to talk about the number n, which is just a product of these two primes, p times q. All right, so now we know how to generate a key. Now we need to figure out, well, this is at least part of a key. Now we're going to have to figure out how we're going to encrypt and decrypt messages. And the way we're going to encrypt and decrypt messages is by exponentiating numbers modulo this number n. So it seems a little weird, but let's sort of go with it for a second. So if you want to encrypt a message, then we're going to take a message m and transform it into m to the power e mod n. So e is going to be some exponent. We'll talk about how to choose it in a second. But this is how we're going to encrypt a message. We'll just take this message as an integer number and just exponentiate it. And then we'll see why this works in a second. But let's call this guy C, ciphertext. Then to decrypt it, we're going to somehow find an interesting other exponent where you can take a ciphertext C, and if you exponentiate it to some power d mod n, then you'll magically get back the same message m. So this is the general plan. To encrypt, you exponentiate. To decrypt, you exponentiate by another exponent. And in general, it seems a little hard to figure out how we're going to come up with these two magic numbers that somehow end up giving us back the same message. But it turns out that if you look at sort of how exponentiation works or multiplication works modulo this number n, then there's this cool property that if you have any number x and you raise it to what's called the earlier phi function of n, sorry, well, maybe I'll use more board space for this. This seems actually important. So if you take x and you raise it to phi of n, then this is going to be equal to 1 mod n. And this phi function for our particular choice of n is pretty straightforward. It's actually p minus 1 times q minus 1. So this sort of gives us hope that maybe if we pick ED so that E times D is 5n plus 1, then we're in good shape. Because then any message M, we exponentiate it to E and D, we get back 1 times M, because our ED product is going to be roughly 5n plus 1, or maybe some constant, alpha times 5n plus 1. So does it roughly make sense? This is sort of why the message is going to get decrypted correctly. And turns out that there's a reasonably straightforward algorithm if you know this phi value for how to compute D given an E or E given a D. All right, question?
Wait, isn't 1 mod n just 1?
Yeah, so that's why we add one more. Sorry?
Up over there.
Yeah, this one?
Yeah.
Yeah. Isn't 1 mod n just 1? Yeah, sorry, I mean this. So when I say this mod n, it means that both sides taken mod n are equal. So what this means is, if you want to think of mod as literally an operator, you would write, okay, this guy mod n equals 1 mod n. So that's what sort of mod n on the side means. Like the whole equality is mod n. Yeah, sorry for the notation. Yeah. Sense? All right. So what this basically means for RSA is that we're going to pick some value E. So E is going to be our encryption value. And then from E, we're going to generate D to be basically 1 over E mod phi of n. And there are some Euclidean algorithms you can use to do this computation efficiently. But in order to do this, you actually have to know this phi of n, which requires knowing the factorization of our number n into P and Q. All right, so finally, so RSA ends up being sort of a system where the public key is this number n and this encryption exponent E. So n and E are public, and D should be private. So then anyone can exponentiate a message to encrypt it for you, but only you know this value D, and therefore can decrypt messages. And as long as you don't know this factorization of P and Q, or of n into P and Q, then you don't know what this phi value is. And as a result, it's actually kind of difficult to compute this D value. So this is roughly what RSA is at a high level. Does this roughly make sense? All right. So there's two things I want to talk about now that we at least have the basic notation for RSA. There's sort of tricks to use it correctly and sort of pitfalls in how to use RSA. And then there's all kinds of implementation tricks of how do you actually implement sort of code to do these exponentiations and do it efficiently. And it's actually non-trivial because these are all large numbers. These are 1,000-bit integers that you can't just do a multiply instruction for. Probably going to take the CPU a fair amount of time to do these operations. All right. So the first thing I want to mention is sort of various RSA pitfalls. One of them we're actually going to rely on in a little bit. So one property is that it's multiplicative. So what I mean by this is that suppose we have two messages. Suppose we have M0 and M1. And suppose I encrypt these guys. So I encrypt M0. I'm going to get M0 to the power E mod n. And if I encrypt M1, then I get M1 to the E mod n. The problem is that, or not necessarily a problem, but could be a surprise to someone using RSA, it's very easy to generate an encryption of M0 times M1, because you just multiply these two numbers. So if you multiply these guys out, you're going to get M0 M1 to the E mod n. This is a correct encryption under this simplistic use of RSA for the value M0 times M1. I mean, at this point, it's not a huge problem because you aren't able to decrypt it. You're just able to construct this encrypted message. But it might be that the overall system maybe allows you to decrypt certain messages. And if it allows you to decrypt this message that you construct yourself, maybe you can now go back and figure out what were these messages. So it's maybe not a great plan to sort of be ignorant of this fact. So this has certainly come back to bite a number of protocols that use RSA. That's one property. We'll actually use it as a defensive mechanism towards the end of the lecture. Another property of RSA that you probably want to watch out for is the fact that it's deterministic. So in this naive implementation that I described here, if you take a message m and you encrypt it, you're going to get m to the e mod n, which is a deterministic function of the message. So if you encrypt it again, you'll get exactly the same encryption. This is not surprising, but it might not be a desirable property, because if I see you send some message encrypted with RSA, and I want to know what it is, it might be hard for me to decrypt it, but I could try different things, and I can see, well, are you sending this message? I'll encrypt it and see if you get the same ciphertext. And if so, I'll know, oh yeah, that's what you encrypted. Because all I need to encrypt a message is the publicly known public key, which is n and the number e. So that's not so great. And you might want to watch out for this property if you're actually using RSA. So all these sort of primitives are probably a little bit hard to use directly. What people do in practice in order to avoid these problems with RSA is they encode the message in a certain way before encrypting it. So instead of directly exponentiating a message, they actually take some function of a message, and then they encrypt that, mod n. And this function f, the sort of right one to use these days, is probably something called optimal asymmetric encryption padding, OAEP. You can sort of look it up, but it's some encoding that has two interesting properties. First of all, it injects randomness. So you can sort of think of f of m as generating a 1,000-bit message that you're going to encrypt. Part of this message is going to be your message m in the middle here, so that you can get it back when you decrypt, of course. But there's two interesting things you want to do. You want to put in some randomness here, some value r, so that when you encrypt the message multiple times, you'll get different results out each time. So then it's not deterministic anymore. And in order to defeat this multiplicative property and other kinds of problems, you're going to put in some fixed padding here. You can sort of think of this as maybe an alternating sequence of 1, 0, 1, 0, 1, 0. You can do better things, but roughly it's some predictable sequence that you put in here, and whenever you decrypt, you make sure the sequence is still there. If you did multiplication, then it's going to destroy this bit pattern, and then you should declare that, oh, someone tampered with my message and reject it. And if it's still there, then presumably, sometimes provably, no one tampered with your message, and as a result, you should be able to accept it and treat message m as being correctly encrypted by someone. Make sense? Yeah?
If the attacker knows how big the pad is, can't they put a 1 in the lowest place and then a bunch of zeros so that you duplicate the pad under multiplication?
Yeah, maybe. It's a little bit tricky because this randomness is going to bleed over. So the particular construction of this OAEP is a little bit more sophisticated than this. But if you imagine, this is like integer multiplication, not sort of bitwise multiplication. And so this randomness is going to bleed over somewhere, and it's you can construct an OAEP scheme such that this doesn't happen. This is a somewhat simplified version. Make sense? All right. So it turns out, basically, you shouldn't really use this RSA math directly. You should use some library in practice that implements all these things correctly for you and use it just as an encrypt-decrypt primitive. But it turns out these details will come in and matter for us because we're actually trying to figure out how to break or how to attack an existing RSA implementation. So in particular, the attack from this paper is going to exploit the fact that the server is going to check for this padding when they get a message. So this is how we're going to time how long it takes a server to decrypt. We're going to send some random message or some carefully constructed message, but the message wasn't constructed by taking a real m and encrypting it. We're going to construct a careful ciphertext integer value. And the server is going to decrypt it. It's going to decrypt to some nonsense, and the padding is going to not match with a very high probability, and immediately the server is going to reject it. And the reason this is going to be good for us is because it will tell us exactly how long it took the server to get to this point, to just do the RSA decryption, get this message, check the padding, and reject it. So that's what we're going to be measuring in this attack from the paper. That make sense? So there's some integrity component to the message that allows us to time the decryption leading up to it. All right. So now let's talk about how do you actually implement RSA. So the core of it is really this exponentiation, which is not exactly trivial to do, as I was mentioning earlier, because all these numbers are very large integers. So the message itself is going to be, at least in this paper, a 1,000-bit integer. And the exponent itself is also going to be pretty large. The encryption exponent is at least well known, but the decryption exponent better be also a large integer, also on the order of 1,000 bits. So if you have a 1,000-bit integer, you want to exponentiate it to another 1,000-bit integer power, modulo some other 1,000-bit integer n. That's going to be a little messy if you just do the naive thing. So almost everyone has lots of optimizations in their RSA implementations to make this go a little bit faster. And there's sort of four optimizations that matter for the purpose of this attack. There's actually more tricks that you could play, but the most important ones are these. So first, there's something called the Chinese remainder theorem, or CRT. And just to remind you from like grade school or something, high school maybe, what this remainder theorem says, it actually says that if you have two numbers, and so if you have some value x, and you know that x is equal to a1 mod p, and you know that x is equal to a2 mod q, where p and q are prime numbers, and this is, this modular equality applied to the whole equation, then it turns out that there's a unique solution to this mod pq. So there's some, x equals to some x prime mod pq. And in fact, there's a unique such x prime, and it's actually very efficient to compute. So the Chinese remainder theorem sort of also comes with an algorithm for how do you compute this unique x prime that's equal to x mod pq, given the values a1 and a2 mod p and q, respectively. Does that make sense, roughly? OK, so how could you use this Chinese remainder theorem to speed up modular exponentiation? So the way this is going to help us is that, if you notice, all the time we're doing this computation of some bunch of stuff modulo n, which is p times q. And the Chinese remainder theorem says that if you want the value of something mod p times q, it suffices to compute the value of that thing mod p and the value of that thing mod q, and then use the Chinese remainder theorem to figure out the unique solution to what this thing is mod p times q. All right, why is this faster? Seems like you're basically doing the same thing twice, and then some more work to recombine it. Is this going to save anything? Yeah.
If P and Q are small enough to fit inside machine size types?
Well, they're certainly smaller. They're not that small, right? So n is 1,000 bits. P and Q are both 500 bits. So they're not quite to the machine word size yet. But it is going to help us because most of the stuff we're doing in this computation is all these multiplications. And roughly, multiplication is quadratic in the size of the thing you're multiplying. Because, the sort of grade school method of multiplication, you take all the digits and you multiply it by all the other digits in the number. And as a result, doing exponentiation and multiplication is roughly quadratic in the input size. So if we shrink the value of p, we basically go from 1,000 bits to 512 bits. We've reduced the size of our input by 2. So this means that all this multiplication exponentiation is going to be roughly 4 times cheaper. So even though we do it twice, each time is 4 times faster. So overall, this CRT optimization is going to give us basically a 2x performance boost for doing any RSA operations, both on the encryption and decryption side. That makes sense, roughly? All right. So that's the sort of first optimization that most people use. The second thing that most implementations do is a technique called sliding windows. And we'll sort of look at this optimization in 2 steps. So this optimization is going to be concerned with what basic operations are going to perform to do this exponentiation. So suppose you have some ciphertext C that's now 500 bits because we're now doing mod P or mod Q. So we have that 500-bit C, and similarly, roughly a 500-bit D as well. So how do we raise C to the power D? I guess the completely stupid way to do it is to take C and keep multiplying it D times. But D is very big, it's 2 to the 500. So that's never going to finish. So a more amenable or more performant plan is to do what's called repeated squaring. So that's sort of the step before sliding windows. So this technique called repeated squaring kind of looks like this. So if you want to compute C to the power 2x, then you can actually compute C to the x and then square it. So in our naive plan, computing C to the 2x would have involved us making twice as many iterations of multiplying because it's multiplying C twice as many times. But in fact, you can be clever and just compute C to the x and then square it later. So this works well, and this means that if you're computing C to some even exponent, this works. And conversely, if you're computing C to some 2x plus 1, then you can imagine this is just C to the x squared times another C. So this is what's called repeated squaring. And this now allows us to compute these exponentiations or modular exponentiations in a time that's basically linear in the size of the exponent. So for every bit in the exponent, we're going to either square something or square something and do an extra multiplication. So that's sort of the plan for repeated squaring. So now we can at least have non-embarrassing runtimes for computing modular exponents. Does this make sense? Why this is working and why it's faster? All right, so what's the sliding windows trick that the paper talks about? So this is a little bit more sophisticated than this repeated squaring business. And basically, the squaring is going to be pretty much inevitable. But what the sliding windows optimization is trying to do is reduce the overhead of multiplying by this extra C down here. So suppose if you have some number that has several 1 bits in the exponent, for every 1 bit in the exponent in the binary representation, you're going to have to do this step instead of this step. Because for every sort of odd number, you're going to have to multiply by C. So these guys would like to not multiply by this C as often. So the plan is to pre-compute different powers of C. So what we're going to do is we're going to generate a table that says, well, here's the value of C to the x, C to the 1. Here's the value of C to the 3, C to the 7, and I think in OpenSSL, it goes up to C to the 31st. So this table is going to just be pre-computed when you want to do some modular exponentiation. You're going to pre-compute all the slots in this table. And then when you want to do this exponentiation, instead of doing the repeated squaring and multiplying by this C every time, what you're basically going to do is use a different formula that says, well, if you have C to the 32x plus some y, well, you can do C to the x, and you can do repeated squaring, very much like before. This is to get to 32. There's like 5 powers of 2 here, times C to the y. And C to the y you can get out of this table. So you can see that we're doing the same number of squarings as before here, but we don't have to multiply by C as many times. You're going to fish it out of this table and do several multiplies by C for the cost of a single multiply. Does this make sense? Yeah?
How do you determine x and y in the first place?
How do you determine y?
X and y.
Oh, okay. So yeah, let's look at that. So for repeated squaring, well, actually, in both cases, what you want to do is you want to look at the exponent that you're trying to use in a binary representation. So suppose I'm trying to compute the value of C to the exponent, I don't know, 1, 0, 1, 1, 0, 1, 0. Maybe there's more bits. Okay, so if we want to do repeated squaring, then you look at the lowest bit here, it's 0. So what you're going to write down is this is equal to C to the 1, 0, 1, 1, 0, 1 squared. Okay, so now, if only you knew this value, then you could just square it. Okay, now we're going to compute this guy. So c to the 1, 0, 1, 1, 0, 1 is equal to, well, okay, so here we can't use this rule because it's not 2x. It's going to be 2 to the x plus 1. So now we're going to write, okay, this is c to the 1, 0, 1, 1, 0 squared times another c. Because it's sort of this prefix times 2 plus this 1 at the end. So that's how you fish it out for repeated squaring. And for sliding window, you just grab more bits from the low end. So if you wanted to do the sliding window trick here, instead of taking one c out, suppose we do, instead of this giant table, maybe we do 3 bits at a time. So we go up to c to the 7th. So here, you would grab the first 3 bits, and that's what you would compute here, c to the 101 to the 8th power. And then the rest is c to the 101 power here. It's a little unfortunate these are the same thing, but really there's like more bits here. But here, this is the thing that you're going to look up in the table. This is c to the 5th in decimal. And this is you're going to keep doing the sliding window to compute this value. Make sense? All right, so this just saves on how many times you have to multiply by c by pre-multiplying it a bunch of times. And the OpenSSL guys, at least 10 years ago, thought that going up to 32 power was the best plan in terms of efficiency, because there's some trade-off here, right? You spend time pre-computing a stable, but then if the stable is too giant, you're not going to use some entries, because if you run the stable out to, I don't know, c to the 128, but you're computing just like 512-bit exponents, maybe you're not going to use all these entries, so it's going to be a waste of time. Question?
Other than timing side channels, is there a reason not to compute the table lazily? So you allocate enough memory for 128 entries, and then you just fill them in whenever you end up needing them?
It ends up being the case that you don't want, well, there's 2 things going on. One is that you'll have now code to check whether the entry is filled in or not, and that'll probably reduce your branch predictor accuracy on the CPU, so it'll run slower in the common case, because you keep having to check whether the entry is there. The other slightly annoying thing is it turns out this entry leaks stuff through a different side channel, namely cache access patterns. So if you have some other process on the same CPU, you can sort of see which cache addresses are getting evicted out of the cache or are slower because someone accessed this entry or this entry. And the bigger this table gets, the easier it is to tell what the exponent bits were. Like in the limit, this table is gigantic, and just being able to tell which cache address on a CPU had a miss tells you that the encryption process must have accessed that entry in the table, and tells you that, oh, that long bit sequence appears somewhere in your secret key exponent. So I guess the answer is mathematically you could totally fill this in on demand. In practice, you probably don't want it to be that giant. And also, if it's particularly giant, then you're not going to be able to reuse entries as efficiently as well. You can sort of reuse these entries as you're computing it, right? It's not actually that expensive because you use c to the cubed when you're computing c to the 7th, and so on and so forth. So it's not that bad. Make sense? Other questions? All right. So this is the sort of repeated squaring and sliding window optimization that OpenSSL implements, still does. I don't actually know whether they still have the same size of the sliding window or not, but it does actually give you a fair bit of speed up. So before you had to square for every bit in the exponent, and then you'd have to have a multiply for every 1 bit. So if you have a 500-bit exponent, then you're going to do 500 squarings, and on average, roughly 256 multiplications by c. So with sliding windows, you're going to still do the 512 squarings, because there's no sort of getting around that. But instead of doing 256 multiplies by c, you're going to hopefully do way fewer, maybe something on the order of like 32 maybe multiplies by some entry in this table. So that's sort of the general plan. So that's why it's sort of save something, not as dramatic as CRT, not 2x, but could save you like close to 1.5x maybe. Well, depending on exactly what the numbers look like. Make sense? Other questions about this? All right. So these are the sort of relatively easier optimizations. And then there's two sort of clever tricks playing with numbers for how to do just a multiplication more efficiently. So the first one of these optimizations that we're going to look at, I think I'll erase this board, is called this Montgomery representation. And we'll see in a second why it's particularly important for us. So the problem that this Montgomery representation optimization is trying to solve for us is the fact that every time we do a multiply, we get a number that keeps growing and growing and growing. In particular, both or in sliding windows or in repeated squaring, actually, when you square, you do multiply two numbers together. When you multiply by c to the y, you multiply two numbers together. And the problem is that if the inputs to the multiplication were, let's say, 512 bits each, then the result of the multiplication is going to be 1,000 bits. And then you take this 1,000-bit result and you multiply it again by something like 512 bits. Now it's 1,500 bits, 2,000 bits, 2,500 bits, and it keeps growing and growing. And we really don't want this because multiplication is quadratic in the size of the number we're multiplying. So we have to keep the size of our number as small as possible, which means basically 512 bits, because all this computation is mod p or mod q. Yeah?
What you want finally is just a remainder, so you can just take the remainder after.
That's right, yeah. So the cool thing is that we can keep this number down, because what we do, let's say we want to compute, c to the x, just from this example, squared, squared again, squared again. So what you could do is you compute c to the x, then you take it mod p, let's say, right? Then you square it, then you do mod p again. Then you square it again, and then you do mod p again, and so on. So this is basically what you're proposing. So this is great. And in fact, it keeps the size of our numbers to basically 512 bits, which is as small as we could get. This is good in terms of keeping down the size of these numbers for multiplication, but it's actually kind of expensive to do with this mod p operation. Because the way that you do mod p something is you basically have to do division. And division is way worse than multiplication. I'm not going to go through sort of the various algorithms for division, but it's really slow. You really want to avoid division as much as possible. Because it's not even just sort of a straightforward quadratic thing. You have to do some approximation algorithm, sort of like Newton's method of some sort, and just keep iterating. It's going to be slow. And in the naive implementation, this actually turns out to be the slowest part of doing multiplications. The multiplication is cheap, but then doing mod p or mod q to bring it back down in size is going to be actually more expensive than the multiply. That's actually kind of a bummer. So the way that we're going to get around this is by doing this multiplication in this clever other representation. And I'll sort of show you the trick here. Let's see, bear with me for a second, and then we'll at the end see why it's actually so fast to use this Montgomery trick. And the basic idea is to represent numbers. So these are like regular numbers that you might actually want to multiply. And we're going to have a different representation for these numbers called the Montgomery representation. And the representation is actually very easy. We just take the value a and we multiply it by some magic value r. I'll tell you what this r is in a second. But let's first figure out, if we pick some arbitrary value r, what's going to happen here. So we take two numbers, a and b. Their Montgomery representations are, sort of expectedly. A is AR, B is BR. And if you want to compute the product of A times B, well, in Montgomery space, you can also multiply these guys out. You can take AR, multiply it by BR, and what you get here is AB times R squared. So there's two R's now. That's kind of annoying, but you can sort of divide it back by R, and we get AB times R. So this is probably weird in the sense that why would you multiply by this extra number? But let's first figure out whether this is correct, and then we'll figure out why this is going to be faster. So it's correct in the sense that it's very easy. If you want to multiply some numbers, we just multiply by this R value, and we get the Montgomery representation. Then we can do all these multiplications to these Montgomery forms. And it's just every time we multiply two numbers, we have to divide by r. We'll get the Montgomery form of the multiplication result. And then when we're done doing all of our squarings, multiplication, all this stuff, we're going to move back to the normal, regular form by just dividing by r one last time.
And R, a nice number.
Yeah, so we're going to now pick r to be a very nice number. And in particular, we're going to pick r to be a very nice number to make this division by r very fast. And the cool thing is that if this division by r is going to be very fast, then this is going to be a small number, and we're not going to have to do this mod q very often. In particular, AR, let's say, is also going to be roughly 500 bits, because it's all actually mod p or mod q. So AR is 500 bits. BR is going to be also 500 bits. So this product is going to be 1,000 bits. This R is going to be this nice 500 roughly bit number, same size as p. And if we can make this division to be fast, then the result is going to be roughly a 500-bit number here. So we were able to do the multiply without having to do an extra divide. Dividing by r cheaply gives us this small result, getting us out of doing a mod p for most situations. Okay, so what is this weird number that I keep talking about? Well, r is just going to be 2 to 512. So it's going to be 1 followed by a ton of zeros. So multiplying by it is easy. You just append a bunch of zeros to a number. Dividing, could be easy if the low bits of the result are all zeros, right? So if you have a value that's a bunch of bits followed by 512 zeros, then dividing by 2 to the 512 is cheap. You just discard the zeros on the right-hand side. And that's actually a correct division. Does that make sense? The slight problem is that we actually don't have the zeros on the right-hand side when we do this multiplication. We're going to get, these are like real 512-bit numbers with all the 512 bits used. So this will be a 1,000-bit number with all the bits also sort of set to randomly 0 or 1, depending on what's going on. So we can't just discard the low bits. But the cleverness comes from the fact that the only thing we care about is the value of this thing mod p. So we can always add multiples of p to this value without changing what it's equivalent to mod p. And as a result, we can add multiples of p to get the low bits to be all zeros. So let's look through some simple examples. I'm not going to write out 512 bits on the board, but suppose that here's a sort of a short example. Suppose that we have a situation where our value r is 2 to the 4th. So it's 1 followed by 4 zeros. So this is a much smaller example than the real thing, but let's see actually how this Montgomery division is going to work out. So suppose we're going to try to compute stuff mod q, where q, let's say, is maybe 7. So this is 1, 1, 1 in binary form. And what we're going to try to do is maybe we did some multiplication, and this value AR times BR is equal to this binary representation 1, 1, 0, 1, 0. So this is going to be sort of the value of AR times BR. How do we divide it by R? So clearly the low 4 bits aren't all 0, so we can't just divide it out. But we can add multiples of Q. In particular, we can add 2 times Q. So 2Q is equal to 1, 1, 1, 0. And now what we get is 0, 0, carry a 1, 0, carry a 1, 1, carry a 1, 0, 1. Hope I did that right. So this is what we get. So now we get AR, BR plus 2Q. But we actually don't care about the plus 2Q. It's actually fine, because all we care about is the value mod Q, something, right? And now we're closer. We have 3 0 bits at the bottom. Now we can add another multiple of Q. This time it's going to be probably 8Q. So we add 1, 1, 1 here, 0, 0. And if we add it, we're going to get, let's say, 0, 0, 0 at the end. Add these two guys 0, carry a 1, 0, carry a 1, 1, 1. I think that's right. But now we have our original AR, BR plus 2Q plus 8Q is equal to this thing. And finally, we can divide this thing by r very cheaply, because we just discard the low 4 zeros. Make sense? Question?
Is ARVR always going to end in, I guess, 1024 zeros?
No, and the reason is that okay, here's the thing that's maybe confusing. A was, let's say, 512 bits. Then you multiply it by r. So here, you're right, this value is a 1000 bit number where the high bit is A, the high 512 bits are A, and the low bits are all zeros. But then you're going to do it mod q to bring it down, to make it smaller. And in general, this is going to be the case because it only sort of has these low zeros the first time you convert it. But after you do a couple of multiplications, they're going to be arbitrary bits. So these guys, right, so yeah, I really should have written, mod q here. And you compute this mod q as soon as you do the conversion to keep the whole value small. Make sense? Other question?
Isn't that expensive?
Yeah, so the initial conversion is expensive, or at least it's as expensive as doing a regular modulus during the multiplication. The cool thing is that you pay this cost just once when you do the conversion into Montgomery form. And then, instead of converting it back at every step, you just keep it in Montgomery form. So remember that in order to do an exponentiation to an exponent which has 500 bits, we were saying we were going to have to do, over 500 multiplications, because we have to do at least 500 squarings plus then some. So you do these mod q twice, and then you get a lot of cheap divisions if you stay in this form. And then you do a division by r to get back to this form again. So instead of doing 500 mod q's for every multiplication step, you do it twice mod q, and then you keep doing these divisions by r cheaply using this trick. Question?
So when you're adding the multiples of q and then dividing by r, why are you still maintaining the same mod q?
Because it's actually, mod q means the remainder when you divide by q. So, x plus, y times q, mod q, is just x.
But aren't you dividing by r before you take the mod q?
So in this case, dividing by, so another sort of nice property is that because it's all modulus a prime number, it's also true that if you have x plus yq divided by r, mod q, this is actually the same thing as x divided by r mod q. The way to sort of think of it is that there's no real division in modular arithmetic, it's just an inverse. So what this really says is this is actually x plus yq times some number called r inverse, and then you compute this whole thing mod q. And then you can sort of think of this as, well, x times r inverse mod q plus yq r inverse mod q. And this thing cancels out because it's something times q. Make sense? All right. And there's some closed form for this thing. So here I did it like bit by bit. Okay, well, 2q, then 8q, etc. There's actually a nice closed formula that you can compute. It's in the lecture notes, but it's not probably worth spending time on the board here for how do you figure out what multiple of q should you add to get all the low bits to turn to 0. So then it turns out that in order to do this division by r, you just need to compute this magic multiple of q, add it, and then discard the low bits. And that brings your number back to 512 bits, or whatever the size is. Make sense? Okay, and here's the subtlety. Like, the only reason we're talking about this is that there's something funny going on here that is going to allow us to learn timing information. And in particular, even though we divided by r, we know the result is going to be 512 bits. But it still might be greater than q, because q isn't exactly 2 to the 512, it's some 512-bit number. So it might be a little bit less than r. So it might be that after we do this cheap division by r, we might have to subtract out q one more time, because we get something that's small, but not quite small enough. So there's a chance that after doing this division, we maybe have to also subtract q again. And this subtraction is going to be part of what this attack is all about. So it turns out that subtracting this q adds time, and someone figured out, not these guys, but some previous work, actually showed that this probability of doing this thing, this is called an extra reduction. This probability sort of depends on the particular value that you're exponentiating. So if you're computing x to the d mod q, the probability of an extra reduction at some point while computing x to the d mod q is going to be equal to x mod q divided by 2r. All right, so let me just separate out. So if we're going to be computing x to the d mod q, then depending on what the value of x mod q is, whether it's big or small, you're going to have either more or less of these extra reductions. And just to show you where this is going to fit in, this is actually going to happen in the decrypt step. Because during the decrypt step, the server is going to be computing c to the d. And this says that, well, the extra reductions are going to be proportional to how close x, or c in this case, is to the value q. So this is going to be worrisome, right? Because the attacker gets to choose the input c, and the number of extra reductions is going to be proportional to how close the c is to one of the factors, the q. And this is how you're going to tell that, oh, I'm getting close to the q, or I've overshot q. And all of a sudden, there's no extra reductions. It's probably because x mod q is very small, because x is q plus a little epsilon, and it's very small. So that's one part of the timing attack we're going to be looking at in a second. Make sense? I don't have any proof that this is actually true, but we'll sort of take it on faith that these extra reductions work like this. Yeah, question?
What happens if you don't do this extra reduction?
What happens if you don't do this extra reduction? Yeah, you know, you can avoid this extra reduction, and then you're just have to do some extra, probably modular reductions later. I think the math just works out nicer this way for the Montgomery form. I think for many of these things, it's actually like once you look at it as a timing channel, then you're thinking, well, yeah, maybe we should just like not do this at all, or maybe we should do some other plan. So you're right. I think you can probably avoid this extra reduction and probably just do the mod q perhaps at the end. I haven't actually tried implementing this, but it seems like it could work. It might be that you just have to do mod q once at the end, which you'll have to probably do anyway. So it's not super clear. Maybe it saves you a little bit of something, but probably not huge. So in light of the fact that this timing attack exists, maybe you should avoid this. But I shouldn't speak authoritatively to this. I haven't actually tried implementing this. So maybe there's some like deep reason why this extra reduction has to happen. I couldn't think of one. But, all right, other questions? All right, so here's the last piece of the puzzle for how OpenSSL, this library that this paper attacks, implements multiplication. So this Montgomery trick is great for avoiding the mod q part during modular multiplication. But then there's a question of how do you actually multiply two numbers together? So we're like going lower and lower level. So suppose you have sort of the raw multiplication. So this is not even modular multiplication. Suppose you have two numbers, a and b. And both these guys are 512-bit numbers. How do you multiply them together when your machine is only a 32-bit machine like the guys in the paper, or 64-bit, but still, same thing. So how would you implement multiplication of these guys? Any suggestions? Well, I guess there's a straightforward plan, which is you just represent A and B as a sequence of machine words, and then you just do this sort of quadratic product of these two guys. So if you just see a simple example, instead of thinking of 512-bit numbers, let's think of these guys as 64-bit numbers, and we're on a 32-bit machine, right? So we're going to have values. The value A is going to be represented by two 32-bit things. That's going to be, let's call it A1 and A0. So A0 is the low bits, A1 is the high bits. And similarly, we're going to represent B as two things, B1, B0. So then a naive way to represent AB is going to be to multiply all these guys out. So it's going to be a 3-cell number, right? The high bit is going to be A1, B1. The low bit is going to be A0, B0. And the middle word is going to be A1, B0 plus A0, B1. So this is how you do the multiplication, right? Make sense? Yeah, question?
So I was going to say, so you're getting to like using Karatsuba's method?
Yeah, so this is sort of like a clever method alternative for doing multiplication, which doesn't involve 4 steps. So here, you got to do 4 multiplications. There's this clever other method, Karatsuba. I don't know, do they teach it in like 601 or something these days?
Over 2.
Over 2, excellent, yeah. That's a very nice method, and almost every cryptographic library implements it. For those of you that, I guess, weren't undergrads here, since we have grad students, maybe they haven't seen Karatsuba, I'll just sort of write it out on the board. It's sort of a clever thing the first time you see it. And what you can do is basically compute out 3 values. You're going to compute A1, B1. You're going to also compute A1 minus B0 times B1 minus, A1 minus A0, B1 minus B0, and A0, B0. And this does 3 multiplications instead of 4. And it turns out you can actually reconstruct this value from these 3 multiplication results. And the particular way you do it is sort of this is going to be the, well, here, let me write it out in a different form. So we're going to have 2 to the 64 times, 2 to the 64 plus 2 to the 32 times A1, B1 plus 2 to the 32 times minus that little guy in the middle, A1 minus A0, B1 minus B0. And finally, we're going to do 2 to the 32 plus 1 times A0, B0. And it's a little messy, but actually if you work through the details, you'll end up convincing yourself, hopefully, that this value is exactly the same as this value. It's a little clever, but nonetheless, it saves you 1 multiplication. And the way you apply this to doing much larger multiplications is that you just recursively keep going down. So if you had 512-bit values, you could break it down to 256-bit multiplication. You do 3 256-bit multiplications, and then each of those you're going to do using the same Karatsuba trick recursively. And eventually you'll get down to machine size, which you can just do with a single machine instruction, and then sort of reconstruct the value at the top. Does this make sense? So what's the timing attack here? How do these guys exploit this Karatsuba multiplication? Well, it turns out that OpenSSL worries about basically 2 kinds of multiplications that it might need to do. One is a multiplication between 2 large numbers that are about the same size. So this happens a lot when we're doing this modular exponentiation, because all the values that we're going to be multiplying are all going to be roughly 512 bits in size. So when we're doing multiplying by c to the y or doing this squaring, we're multiplying 2 things that are about the same size. And then this Karatsuba trick makes a lot of sense, because instead of computing stuff in times squared of the input size, Karatsuba is roughly n to the 1.58, something like that. So it's much faster. But then there's this other situation where OpenSSL might be multiplying 2 numbers that are very different in size, one that's very big and one that's very small. And in that case, you could use Karatsuba, but then it's going to be actually slower than doing the naive thing. Suppose you are trying to multiply a 512-bit number by a 64-bit number. You'd rather just do the straightforward thing where you just multiply by each of the things in the 64-bit number. That's 2n instead of n to the 1.58 something. So as a result, the OpenSSL guys try to be clever, and that's where often problems start. They decided that they'll actually switch dynamically between this Karatsuba efficient thing and this sort of grade school method of multiplication here. And their heuristic was basically, if the 2 things you're multiplying are exactly the same number of machine words, so so they basically have the same number of bits up to 32-bit units, then they're going to do Karatsuba. And if the two things that are multiplying have a different number of 32-bit units, then they'll do the quadratic or sort of straightforward, regular, normal multiplication. And there you could sort of see, well, if your number all of a sudden, switches to being a little bit smaller, then you're going to switch from this efficient thing to this other multiplication method. And presumably, the cutoff point isn't going to be exactly smooth, so you'll be able to tell, all of a sudden, it's now taking a lot longer to multiply or a lot shorter to multiply than before. And that's what these guys sort of exploit in their timing attack again. That make sense? What's going on with those multiplies? All right. So I think I'm now done with sort of telling you about all the weird implementation tricks that people play when implementing RSA in practice. So now let's try to put them back together into an entire web server and figure out how do you, tickle all these interesting bits of the implementation from the input network packet. So what happens in a web server is that the web server, if you remember from the HTTPS lecture, has a secret key. And it uses the secret key to prove that it's the correct owner of that certificate in this HTTPS protocol, or in TLS. And the way this works is that the client sends some randomly chosen bits, and the bits are encrypted using the server's public key. And the server in this TLS protocol decrypts this message, and if the message checks out, it uses those random bits to establish a session key. But in this case, the message isn't going to check out. The message is going to be carefully chosen, the padding bits aren't going to match, and the server is going to return an error as soon as it finishes decrypting our message. And that's what we're going to time here. So the server, you can sort of think of it as this is, Apache with OpenSSL. It's going to get a message from the client, and you can sort of think of this as a ciphertext C, or a hypothetical ciphertext that the client might have produced. And the first thing we're going to do with the ciphertext C, we want to decrypt it using roughly this formula. And if you remember, the first optimization we're going to apply is the Chinese remainder theorem. So the first thing we're going to do is basically split our pipeline into two parts. We're going to do one thing mod P, another thing mod Q, and then recombine the results at the end of the day. So the first thing we're going to do is we're actually going to take C, and we're going to compute, let's call this C0, which is going to be equal to C mod Q. And we're also going to have a different value, let's call it C1, which is going to be C mod P. And then we're going to do the same thing to each of these values to basically compute C to the D mod P and C to the D mod Q. And here we're going to basically, initially we're going to start sort of after CRT, we're going to switch into Montgomery representation because that's going to make our multiplies very fast. So the next thing OpenSSL is going to do to your number, it's actually going to compute, I'll denote it C0 prime, which is going to be C0 times R mod Q. And the same thing down here. I'm not going to write out the bottom pipeline, it's exactly the same. And then, now that we've switched into Montgomery form, we can finally do our multiplications. And here's where we're going to use the sliding window technique. So once we have C prime, we can actually try to compute the C prime exponentiated to D mod Q. And here, as we're computing this value to the D, we're going to be using sliding windows. So here, we're going to do sliding windows for the bits in this D exponent. And also, we're going to do Karatsuba or regular multiplication, depending on exactly what the sizes of our operands are. So if it turns out that the thing we're multiplying, C0 prime, and maybe the previously squared result are the same size, we're going to do Karatsuba. If C0 prime is tiny, but some previous thing we're multiplying it to is big, then we're going to do sort of quadratic multiplication, normal multiplication. So there's sort of sliding windows coming in here. Here we also have this Karatsuba versus normal multiply. And also in this step, the extra reductions come in, because at every multiply, the extra reductions are going to be proportional to the thing we're exponentiating mod q. So just to sort of plug in that formula over here, the probability of extra reduction is going to be proportional to the value of C0 prime mod q divided by 2r. Make sense? So this is where the really timing sensitive bit is going to come in. And there's actually two effects here. There's this Karatsuba versus normal choice, and then there's the number of extra reductions you're going to be making. But okay, so we'll see how we exploit this in a second, but now that you get this result, for mod q, you're going to get a similar result mod p. You can finally recombine these guys from the top and the bottom, and sort of use CRT, and what you get out from CRT is, actually, sorry, I guess we need to first convert it back down into non-Montgomery form. So we're going to get, first we're going to get C0 prime to the d divided by r mod q. And this thing, because C0 prime was C0 times r mod q, if we do this, then we're going to get back out our value of c to the d mod q. And we get c to the d mod q here. We're going to get c to the d mod p on the bottom version of this pipeline. And we can use CRT to get the value of c to the d mod n. Sorry for the small type here, or font size, but roughly it's the same thing we're expecting here. We can finally get our result, and we get our message m. So the server takes an incoming packet that it gets, runs it through this whole pipeline, does two parts of this pipeline, ends up with a decrypted message m that's equal to c to the d mod n, and then it's going to check the padding on this message. And in this particular attack, because we're going to carefully construct this value c, the padding is going to actually not match up. We're going to choose the value c according to some other heuristics that aren't encrypting a real message with the correct padding. So the padding is going to be a mismatch, and the server is going to immediately report an error back to the client and close the connection. And that's the time that we're going to measure to figure out how long this whole pipeline took. Does that make sense? Any questions about this pipeline, putting all these optimizations together?
Isn't that C0 to the d mod q and C1 to the d mod q when you assemble them back?
Yeah, you're probably right. Yeah, C1 to the D, C0 to the D. Yeah, right. This is C0. Yeah, you're right. Question?
When you divide by r mod q, isn't there uncertainty in how many q's you have to add to get the locus to be 0, and also is there an extra reduction?
Yeah, so there might be extra reductions in this final phase as well. You're right. So potentially, we have to do this divide by r correctly. So we probably have to do exactly the same thing as we saw for the Montgomery reductions here when we do this divide by r to convert it back. So it's not clear exactly how many q's we should add. We should figure out how many q's to add that many, kill the low zeros, and then do mod q again, maybe an extra reduction. So you're absolutely right. This is exactly the same kind of divide by r mod q as we do for every Montgomery multiplication step. Make sense? All right. Any other questions? All right. So how do we exploit this? How does an attacker actually figure out what the secret key of the server is by measuring the time of this entire pipeline? So these guys have a plan that basically involves guessing one bit of the private key at a time. And what they mean actually by guessing the private key is that you might think the private key is this decryption exponent d, because actually you know E, you know N, that's the public key. The only thing you don't know is D. But in fact, in this attack, they don't go for the exponent d directly. That's a little bit harder to guess. Instead, what they're going to go for is the value q or the value p, doesn't really matter which one. Once you guess what the value p or q is, then you can, given n, you can factor it into p times q. Then if you know p times q, you can actually, if you know the values p and q, you can compute that phi function we saw before, It's going to allow you to get the value d from the value e. So this factorization of the value n is hugely important. It should be secret for RSA to remain secure. So these guys are actually going to go and try to guess what the value of q is by timing this pipeline. All right. So how do these guys actually do it? Well, they construct carefully chosen inputs C into this pipeline, and I guess I keep saying they keep measuring the time for this guy. But the particular, there's two parts of the attack. You have to sort of bootstrap it a little bit to guess the first couple of bits, and then once you have the first couple of bits, you can sort of guess the next bit. So let me not say exactly how they guess the first couple of bits, because it's actually much more interesting to see how they guess the next bit. And then we'll come back if we have time to look at how do they guess the first couple of bits. They say it in the paper. But basically, suppose you have a guess g about what the bits are of this value q. So you know that q has some bits, g0, g1, g2, etc. And actually, I guess these are not even g's, these are the real q bits. So let me sort of write it as that. So you know that q bit 0, q bit 1, q bit 2, these are the highest bits of q. And then you're trying to guess lower and lower bits. So suppose you know the value of q up to bit j. And from that point on, your guess is actually all zeros. You have no idea what the other bits are. So these guys are going to try to get this guess g into this place in the pipeline, because this is where there's two timing effects, this choice of Karatsuba versus normal multiplication, and this choice of, or this different number of extra reductions depending on the value of C0 prime. So they're going to actually try to get two different guess values into that place in the pipeline, one that looks like this, and one that they call G high, which is all the same high bits, Q2, Qj, and for the next bit, which they don't know, guess G is going to have 0, G high is going to have a bit 1 here, and all zeros later on. So how does it help these guys figure out what's going on? So there's really sort of two ways you can sort of think of it. Suppose that we get this guess G to be the value of C0 prime. So you can sort of think of this G and G high being the C0 prime value on that left board over there. It's actually fairly straightforward for them to do this, right? Because C0 prime is pretty deterministically computed from the input ciphertext C0. You just multiply it by R. So in order for them to get some value into here as a guess, they just need to take their guess and first divide it by R. So divided by 2 to the 512 mod something. And then they're going to inject it back. And the server is going to multiply by R. And off you go. Make sense? All right. So suppose that we manage to get our particular chosen integer value into that C0 prime spot. So what's going to be the time to compute C0 prime to the D mod Q? So there's two possible sort of options here where Q falls in this picture. So it might be that Q is sort of between these two values because the next bit of Q is 0. So this value is going to be less than Q, but this guy is going to be greater than Q. So this happens if the next bit of Q is 0. Or it might be that Q lies above both of these values if the next bit of Q is 1. So now we can try to tell, okay, like what's going to be the timing of decrypting these two values if Q lies in between them or if Q lies above both of them. So let's look at the situation where Q lies above both of them. Well, in that case, actually everything is pretty much the same, right? Because both of these values are smaller than Q, then the value of these things mod Q is going to be roughly the same. They're going to be a little bit different because it's an extra bit, but more or less they're sort of the same magnitude. And the number of extra reductions is also probably not going to be hugely different because it's proportional to the value of this guy mod Q. And for both of these guys, they're both a little bit smaller than Q, So they're all about the same, right? Neither of them is going to exceed Q and all of a sudden have many fewer extra reductions. So if Q is greater than both of these guesses, then Karatsuba versus normal is going to stay the same. The server is going to do the same thing basically for both G and G high in terms of Karatsuba versus normal. And the server is going to do about the same number of extra reductions for both these guys as well. So if you see that the server is taking the same amount of time to respond to these guesses, then you should probably guess that, oh, Q probably has the bit 1 here. On the other hand, if Q lies in the middle, then there's two possible things that could sort of trigger and change the timing. One possibility is that because G high is just a little bit larger than Q, then the number of extra reductions is going to be proportional to this guy mod Q, which is very small, because C0 prime is Q plus just a little bit in these extra bits. So the number of extra reductions is going to plummet, and all of a sudden it will be faster. Another possible thing that could happen is that maybe the server will decide, oh, now it's time to do normal multiplication instead of Karatsuba. Maybe, for this value, all these C to the 0 prime was the same number of bits as Q. If it turns out that G high is above Q, then G high mod Q is potentially going to have fewer bits, and if this crosses a 32-bit boundary, then the server is going to do normal multiplication all of a sudden. So that's going to be sort of in the other direction. So if you cross over, then normal multiplication kicks in, and things get a lot slower because normal multiplication is quadratic instead of nicer, faster Karatsuba. Question?
Can you imply the number of extra reductions?
Yeah, because the number of extra reductions is proportional to, from above there to C0 prime mod Q. So if C0 prime, which is this value, is just a little over Q, then this is tiny. As opposed to this guy, it's basically the same as Q, or all the high bits are the same as Q. And then it's big. So then there'll be this difference that you can try to measure. So there's one interesting thing, actually a couple of interesting things. These effects actually work in different directions, right? So if you hit a 32-bit boundary and Karatsuba versus normal switches, then all of a sudden it takes much longer to decrypt this message. On the other hand, if it's not a 32-bit boundary, maybe this effect will sort of tell you what's going on. So you have to actually watch for different effects. So if you're not guessing a bit that's a multiple of 32 bits, then you should probably expect the time to drop because of extra reductions. On the other hand, if you're trying to guess a bit that's a multiple of 32, then maybe you should be expecting for it to jump a lot, or maybe drop if it's already normal. So I guess what these guys look at in the paper is they say actually it doesn't really matter whether there's a jump up or a jump down in time. You should just expect if the next bit of Q is 1, you should expect these things to take almost the same amount of time. And if the next bit of Q is 0, then you should expect these guys to have a noticeable difference, even if it's big or small, even if it's positive or negative. So they actually sort of measure this, and it turns out to actually work pretty well. They have to do actually two interesting tricks to make this work out. If you remember, the timing difference was tiny. It's an order of 1 to 2 microseconds. So it's going to be hard to measure this over a network, over an Ethernet switch, for example. So what these do is they actually do two kinds of measurement, two kinds of averaging. So for each guess that they send, they actually send it several times. And in the paper they say they send it like 7 times or something. So what kind of noise do you think this helps them with if they just like resend the same guess over and over? Yeah?
Well, it helps them with the jitter that there might be in the latency.
Yeah, so if the network keeps adding different latency, you just try the same thing many times. The thing at the server should be taking exactly the same amount of time every time. They just average out the network noise. And in the paper they say they take the median value. I actually don't understand why they take the median. I think they should be taking the min. That's the real thing that's going on. But anyway, this lets them average out the network noise. But then they do this other weird thing, which is that when they're sending a guess, they don't just send the same guess 7 times. They actually send a neighborhood of guesses, and each value in the neighborhood gets sent 7 times itself. So they actually send G 7 times, then they send G plus 1, also 7 times, then they send G plus 2, also 7 times, etc., up to G plus 400 in the paper. Why do they do this kind of averaging as well over different G values instead of just sending G 7 times 400 times? It seems more straightforward, yeah?
Maybe average out over noise induced by other
Yeah, so actually what's going on, right, is like we're actually trying to measure exactly how long this piece of the computation will take. But then there's lots of other stuff. For example, this other pipeline that's at the bottom is doing all the stuff mod p. I mean, it's also going to take different amounts of time depending on what exactly the input is. So the cool thing is that if you perturb the value of your guess g by adding 1, 2, 3, whatever, it's just going to twiddle the low bits. So the timing attack we just looked at just now isn't going to change because that depended on this middle bit flipping. But everything that's happening on the bottom side of the pipeline, mod p, is going to be totally randomized by this, because when you do it mod p, then adding an extra bit could shift things around quite a bit, mod p, and you're not going to, it'll average out other kinds of sort of computational noise that's deterministic for a particular value, but it's not related to this part of the computation we're trying to go after. Make sense?
How do they do that when they try to guess the lower bits?
So actually, they use some other mathematical trick to only actually bother guessing the top half of the bits of Q. It turns out if you know the top half of the bits of Q, there's some math you can rely on to factor the numbers, and then you're in good shape. So you can always twiddle the low bits and basically not worry about it. Make sense? Yeah, question? Well, you're going to construct this value C0, well, you want the C0 prime. You're going to construct a value C by basically taking your C0 prime and multiplying it times R inverse mod n. And then when the server takes this value, it's going to push it through here. So it's going to compute C0. It's going to be C mod Q. So that value is going to be C0 prime R inverse mod Q. Then you multiply it by R, so you get rid of the R inverse. And then you end up with the guess exactly in this position. So the cool thing is basically all the manipulations leading up to here are just multiplying by this R, and you know what R is going to be. It's going to be 2 to the 512. That's going to be relatively straightforward to do. Make sense? Other questions? Yeah?
Could we just cancel out timing from the bottom of the pipeline by making change the value of multiple of Q, multiple of P?
Well, if you knew P, you'd be in business. Yeah, so that's the thing, yeah. So you don't know what P is, but you just want to sort of randomize it out, yeah. That's good. Other questions? All right, well, we ran over a little bit, but thanks for sticking around. So we'll start talking about other kinds of problems next week. See you guys then.